So today we're going to spend some time talking about square and cubic units, continuing our metric conversions. So for a rectangle, we know that area is length times width. So for something simple like this, for this pretty simple box here, let me turn on the pen. The area would be 4 meters times 2 meters, which of course is 8. But now we've got meters times meters. I'm sorry for that little pen spike. It's something in PowerPoint and Windows 10. Is 8 meters squared. And area is a square unit. So you could have meter squared, centimeter squared, kilometer squared. Now a lot of people think that because there's 100 centimeters in a meter, that you have 100 square centimeters in a square meter. And that's not true. So a square centimeter is just this tiny little bit right here. Now, I didn't draw 100 boxes, you'll have to imagine. But if I stacked up 100 square centimeter boxes, they would fill this tiny little ribbon like I have in the picture here. There's no way they would fill out the whole meter. Because if this is 100 centimeters, and this is 100 centimeters, well, 100 times 100 is 10,000. So 1 square meter is 10,000 square centimeters. And volume gets even worse, or more complex, because volume is a cubic unit. So here, you can see we have a rectangular cube, or not a cube, but a rectangular solid. So its volume would be length times width times height, or 2 times 4 times 9, which is 72. But centimeters, there's 3 of them. That's centimeters cubed. So my goal in this video is just to show you a few conversions here. Now, before we do that, let's talk about what a milliliter actually is. A milliliter is actually a cubic centimeter. So if you can imagine a little cube, a centimeter by centimeter by centimeter, that's actually a milliliter. So on medical shows, they'll say, give the person so many cc's, or maybe you have a doctor or nurse in your family. Give them so many cc's of this particular medication. What they really mean is cubic centimeter. Now, something you might know that's a cubic centimeter or about is little cubed carrots. Like sometimes they're in, if you get a carrot and peas mixture, and they have the little carrot cubes in there. Those little carrot cubes are about a cubic centimeter. Now, a liter is a cubic decimeter. It's 1 decimeter by 1 decimeter by 1 decimeter, or roughly 10 centimeters on a side. So, to get an idea of, well, how much is that? Imagine a 2-liter soda bottle. Now, let's have one that's empty. If you cut it in half, well, that's a liter. Now, it's not cubic shaped, but it actually would be the same volume as 10 centimeters by 10 centimeters by 10 centimeters. Or you can imagine a cube about the width of your palm. So it would be that wide, that tall, and that deep. So let's do some conversions. So let's see how many square decimeters is 0.250 meters squared. So we want to go from meters squared to decimeters squared. And we know that there's 10 decimeters in a meter. The problem is that'll only cancel one of our meters. Just treat the m squared the same way you would treat or think about x squared in algebra. It wouldn't fully cancel. So what we're going to have to do is do it 2 times. That way meters times meters is meters squared, and that will cancel. Then decimeters times decimeters is decimeters squared. So we're going to multiply it by 10 twice. And we get 25 decimeters squared. Let's try another one. Now let's do one with cubic units. So we're going to have 0.00452 meters cubed. We want to go to centimeters cubed. So we know 100 centimeters in a meter, just like 100 years in a century. But if that were like m squared, or m cubed, if that were just a variable like x cubed in algebra, these wouldn't cancel. M could only bring that down to 2. Because it's cubic, because it's to the third, we need to do it 3 times. Then the meters cubed. And you see centimeters, centimeters, centimeters. So we multiply by 100 times 100 times 100, and we get centimeters cubed. And you could think of it as you're moving the decimal 6 places if you want to count the zeros. Now, sometimes students will say, well, can I do that quicker? Can I write that a little quicker? And let's see. Meters cubed. You could write it, and sorry about that little spike there. I have to figure out how to get rid of that. You could write it that way, but you have to remember to cube the 100 before you do any of the other math. Now, these are some practice ones that we're going to do in class together. And then I'll just give you a little bit of an introduction of what we're going to talk about next, which is scientific notation. Now, scientific notation's been around a long time. It's actually been around since 1637. And it was first proposed by the French mathematician and philosopher René Descartes. Looks like Descartes, but it's Descartes is how you say it. Now, he's best known for his philosophy, where he has his famous quote, maybe you've heard it, "I think, therefore I am." Which is sort of like, what separates us from the animals, that we're self-aware. We think and we know that we exist. And he came up with this idea of using powers of 10 for really big or really small numbers. So how does this work? Well, 10 raised to the 0 is 1. In fact, anything raised to the 0 is 1. 10 to the first is 10. 10 squared is 10 times 10, or 100. And then 10 to the third is 10 times 10 times 10, or 1,000. So if you notice, the exponent is the number of zeros here. There's no zeros here. There's 1 0 here. 2 zeros, 2 zeros. 3 zeros, 3 zeros. So who uses scientific notation? Astronomers really, really need it. For example, there are 200 billion stars in the Andromeda Galaxy. Now, the Andromeda Galaxy is the one that's nearest our own, which is the Milky Way. It's really our next-door neighbor galaxy. And that's a really big number. So big that we don't want to write it all the time. So what we do is we count the zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 zeros. And so what I can do is rewrite it as 2 times 100 billion. You might say, well, that doesn't seem any better. In fact, it seems worse. But we counted zeros. We know there are 11 zeros. So because there are 11 zeros, we can rewrite it as 2 times 10 to the 11th stars. That's a lot easier. Astronomers use this all the time because they work with such big numbers. You might say, well, we're not doing astronomy. This is chemistry class. Sure. Well, it turns out that helium is a really, really small atom, and all atoms are really small. And that's what it is in grams. I guarantee if I had to type that into the calculator a number of times, every time I was doing something with the helium atom in chemistry, I'm a chemist, so we work with atoms all the time, I guarantee I'd forget a few zeros. So it's much, much better to use scientific notation. So let's see where that number came from. We start here and we loop over. And if we count zeros, we would get 24. Now it's to the negative 24 because it's a really small number. Another thing to point out, we only have one place in front of the zero usually. I don't want to say it could ever be different because there are times when you might have more than one. But in most standard scientific notation, we would want 6 point something, 4 point something, 8 point something. We wouldn't want 100 point something much of the time. Most of the time, we're going to just have one place after the decimal, and we're going to do more with that another day.